So for the idea of projections, let's say you have a subspace, let's say just a two-dimensional subspace, like a plane. And let's call that subspace S for now. And let's say you have a vector that is not part of that subspace. Let's say you've got some vector V that's not in the plane. The idea of a projection is that we want to create a new vector that is a member of the subspace, but is as close as possible to vector V. That's really what we mean by a projection. The projection of V onto X. The projection of vector V onto S is a new vector that is in set S, subspace S, that is as close as possible to V. Which means we want to create a new vector, some vector in the plane itself. So like these vectors are all in the plane, let's say. But we want to choose one of those vectors in the plane that's as close as possible to the original vector V. And geometrically, how would you do that? How could you geometrically create a vector in the plane that's as close as possible to the vector we've got that's not in the plane?
Do we want it to be like one of the red arrows? Is that what we wanted to?
Well, one of these red arrows, because it's going to be a vector that's in the plane. But first of all, which direction would you want to go? Within the plane, from this as our origin or starting point, which direction would you want to go to get as close as possible to vector V? There is a certain directionality here, because for instance, if you go this way, you're just getting further and further and further from the endpoint of V. If you wanted to get as close as possible to, let's say, specifically the endpoint of V, like instead of considering V as a vector, if you consider V as a point in space, how would you find a point on the plane that's as close as possible to this point in space? Any thoughts on what you could do geometrically to construct a point on the plane that's as close as possible to this point?
Is it like a scalar multiple of the same line?
Well, if we take a scalar multiple of this, it's still going to be off the plane. We want a vector on the plane or a point on the plane as close as possible to this point. But if you think of this geometrically, if you wanted to travel from this point to a point on the plane and travel the shortest distance possible, which direction would give you the shortest possible distance to get from this point to the plane?
Going straight down.
Yeah, in this case, straight down. In other words, creating a line that forms what angle with the plane itself?
90.
Yeah, a right angle. So we would usually describe this process geometrically as dropping a perpendicular or creating what we would call an altitude, a perpendicular line through that plane that goes to that point. And where that altitude, that perpendicular intersects the plane, that's the point on the plane that's closest to this point that's off the plane. So the vector from the origin to that one point, that vector, let's call that vector P for now, that would be the projection of vector V onto subspace S. So you could think of this as taking vector V and sort of flattening it onto the subspace, flattening it onto this plane, or whatever the subspace happens to be. So we call that the projection of vector V onto subspace S. And the notation we usually use for that is we write it as projection on a projection sub S of vector V. So we use essentially function notation for this. You could think of projection onto S as an operation, and you could think of vector V as the input. So we're taking vector v as the input, and we're going through the process of projecting it onto the subspace, flattening it onto this subspace. And the output is a new vector that's a member of the subspace. So this process is called projecting the vector onto subspace S. And the end result should be a new vector that is guaranteed to be a member of the subspace we're talking about and is as close as possible to the original vector. And ultimately, what we mean by as close as possible is all about the difference between the two vectors. This difference is called the error, in the sense of how far off the original is from the projection. And that itself could be written as a vector E. So you could think of this as the original vector equals the projection plus the error. So we're essentially splitting up the original vector into components, a component in the plane itself and an extra component perpendicular to the plane. Or again, it doesn't have to be a plane, whatever subspace we're talking about. So the vector itself can always be written as its own projection plus the error term. And the whole idea of the projection is when we talk about finding the vector closest to the original vector, that just means we're trying to make the error vector as small as possible. And the perpendicular works here because if we had used, say, non-perpendicular, like let's say we made the vector a little shorter, now our error vector would be along this diagonal, and the diagonal is going to be larger than the perpendicular. So we need the error vector to be perpendicular so that it is as small as possible. Any questions on that so far? The geometry of the whole thing. And the subspace we're talking about could be any number of dimensions. Maybe we're talking about a 3-dimensional universe and we're projecting onto a 2-dimensional plane. Or maybe we're talking about a 17-dimensional universe and we're projecting onto a 12-dimensional subspace. Or maybe we're just talking about R2 and we're projecting onto a 1-dimensional line. You could project from some universe onto any subspace of that universe. The 3-dimensional to 2-dimensional is just one example. Probably the easiest to visualize, I would think. But let's take a look at how we would actually calculate this for a lower dimension version. Instead of talking about a whole plane, let's say we're just projecting onto a line. So let's say we have some line. And that line, if we just have a line, that's the span of how many vectors? How many vectors do you need to make a basis for a line?
One.
Yeah, just one. So let's say we describe this line as the span of one single vector. Let's say this is vector S. So the subspace we're talking about is the span of vector S. And let's say we have another vector that is not already a member of that set. Let's say we have this vector. And we'll call this vector V. If we want to create the projection of V onto S, the projection of V onto, and formally it's the projection of V onto the line, projection of V onto the span of vector S. But we usually just write this as the projection of vector V onto vector S. Just keep in mind, this means we're projecting vector V onto the entire line created by vector S. And again, we could think of this as dropping a perpendicular. I guess I should really draw line span S as going out forever in both directions. But we would drop a perpendicular, create an altitude. And the actual projection is going to be a new vector on that line, but that approximates vector V as close as possible. So that would be the projection of V onto the direction of S. Again, thinking of V as the input and projection onto S as the process, the function being done to it. And again, you could think of the difference between them as an error vector. And we want to find a projection, a P vector that makes the difference, the error, as small as possible. And again, geometrically, that means the error vector has to be perpendicular. Any other questions on that so far? And by the way, a very useful way of visualizing this is if you imagine the vector, like let's say you imagine there's a very bright light up here shining perpendicular to the subspace. You could think of the projection as the shadow that the vector casts. Like if I have a vector that's not in the plane of the whiteboard, but we have light shining on it, I guess that's really perpendicular. Let me get a perpendicular here. Light shining on it. Does that work? Kind of difficult to see, I guess. Let me turn off the other light. So if we have some vector that's not part of the marker board, and we shine a light on it perpendicular, it creates a shadow on the marker board. So we say the shadow is the projection of the vector onto the marker board. So that's the sort of geometry we're talking about here. You could think of the projection as a shadow cast onto the plane or the subspace or whatever by the original vector, assuming you've got perpendicular rays of light coming in. Any questions on the geometry there so far? And let me go get the big light again. All right, so let's see how we would actually calculate this. If we have a, let's say we know vector V and we know vector S. That's typically what we know in advance. We have some vector and we have some direction we want to flatten it onto. So we're trying to calculate projection of V onto vector S or onto the direction of S. And let me throw in some actual numbers there. Let's say we've got an XY coordinate plane. So just R2. And let's say vector V is, let me actually throw in some numbers here. Let's say vector V is 3, 4. And let's say we want to create the projection of this vector onto another line. Let's say we want to create the projection of that onto the line formed by, let's say, 4, -1. So this S vector defines an entire direction. And what we want to do is we want to take vector V and flatten it onto vector S to create the projection. So we should expect the result to be a vector in the same direction as S, but maybe in this case, I guess probably shorter. Because dropping it perpendicular here is going to lead to a result that's shorter than the original vector S. And by the way, the size of vector S doesn't really matter. We're just using vector S to define a direction. So its magnitude doesn't really matter so much as the direction does. But let's see if we can actually get a formula for projection of V onto S. First of all, we want the result to be in the same direction as S. Must be parallel to S itself. Without regard to anything else about the projection, if all we want is a vector in the same direction as S, how do you build a new vector that's guaranteed to be in the same direction as S? Or what could you do to vector S that doesn't change the direction? what operation is guaranteed to keep the same direction for a vector?
Multiplying?
Yeah, if we just multiply it by some scalar. So you can always think of a projection as some scalar times vector s. If we want to project onto vector s, the result is always going to be some scalar times vector s. We just need to figure out what that scalar is going to be. So the scalar times s, this is just to make sure we're setting up a new vector that's in the same direction as s, or maybe the exact opposite direction. Like if vector v was over this way, then the projection would be in a direction opposite to vector s. But we can accomplish that just by having this scalar be a negative scalar. To figure out what that scalar is, we're going to need some geometry. First of all, the original vector and its projection and the error form what shape?
Right triangle.
Yeah, it's a right triangle. Because in order to make sure that the projection is as close as possible to v, to make sure the error vector is as small as possible, the error vector must be perpendicular to the subspace we're talking about. So this is going to have to form a right triangle by definition. And if you have a right triangle, let's say we happen to know this angle. Let's call that angle theta. If you know angle theta, how are the original vector and its projection related to each other in terms of size? Based on right triangle trigonometry, if you just have theta and this side, let's call it v, and this side, let's call p for projection, how would you write out the relationship between side v and side p using theta and trigonometry? What trigonometric function is going to relate the adjacent side and the hypotenuse?
Cosine?
Yeah, that should be cosine. We can say cosine of theta is going to be adjacent over hypotenuse, that's p over v, the projection over the original vector in terms of their magnitudes, ignoring direction for now. So if you isolate p, you would get projection magnitude equals original vector magnitude times cosine theta. So that's really the magnitude we want. We want the magnitude of the projection vector to be magnitude of v times cosine theta. So we know the direction for the actual projection itself. The direction needs to be in the same direction as s. And we know the magnitude has to be v cosine theta. Any questions on that so far? And the fact that this is cosine allows us to make use of a very powerful property of dot products. Specifically, if you take the dot product of two vectors, let's say vector s dot vector v. Do you remember how the dot product relates to the angle between the vectors? What's one formula you can use for s dot v?
Are you asking when it's like orthogonal to each other? Or?
You can use this to find whether they're orthogonal or not. When would they be orthogonal? Or what would that tell you about the dot product?
It's equal to 0.
Right. And ultimately that happens because cosine of 90 degrees is 0. One way you can calculate dot product, I mean, usually we calculate dot product by multiplying like x times x plus y times y plus z times z. But that also is always going to equal magnitude of one vector times magnitude of the other vector times cosine of the angle between them. So we can make use of this. We have v cosine theta as the magnitude we want. We want the projection vector to have magnitude v cosine theta to get the trigonometry to work out right here. But v cosine theta also shows up in a formula for dot product. So S dot V, assuming we have vector S and vector V as components, if we take the dot product of S dot V, that tells us magnitude S times magnitude V times cosine theta, and magnitude V times cosine theta is exactly the magnitude we want. The only problem is we've got this extra times magnitude S here. But how could you get rid of times magnitude S? If V cosine theta is the value we want, the magnitude that this side should have, but what we end up with from dot product is S times V times cosine theta, then we have this extra times S we don't want. How do you get rid of an extra times S?
We factor it out.
Well, factoring it out would rewrite it, but how do you get rid of it entirely? What's the opposite of multiplying by S?
Divide.
Yeah, if we just divide both sides of this by magnitude S, which we can do because magnitude of S is a scalar, not a vector. Then what's left after canceling out the magnitude S is V cosine theta. And V cosine theta is exactly the size we need the projection to be. So this tells us that if you take S dot V, but then divide by the magnitude of S, that tells you the magnitude of the projection. So if we fill that in here, if we fill in S dot V divided by magnitude of S, S dot V divided by magnitude of S is the magnitude we need this to have. There's only one slight problem though. If you multiply S dot V over S, the magnitude we want it to have, times S itself, do we still have the correct magnitude? If you've got exactly the magnitude you want, and you multiply it by some vector, does the result have that magnitude you want?
Yes.
For example, in this case, what's the magnitude of this vector S, the 4, -1? How would you calculate the magnitude of this vector?
Is it the square root of 16 plus 1?
Yes,
So
so that'll be square root of 17. So S is a vector whose magnitude is square root of 17. And let's say we find that the magnitude we want is 5. If you take a vector whose magnitude is square root of 17 and multiply by 5, do you get a vector whose magnitude is 5?
no.
Well, yeah, ultimately the problem here is if S dot V over S, that is, S dot V gives you magnitude S times magnitude V times cosine theta, but divide by magnitude S and you get V cosine theta, which is the magnitude we want from trigonometry, then this S dot V over S is exactly the magnitude we want the result to have. But if we multiply that desired magnitude by vector S, the new result doesn't have the correct desired magnitude anymore. It's been multiplied by the magnitude of S itself, in this case, square root of 17. So how do we correct for that? If the result we get there is square root of 17 times too big, how do we correct for that and get back to the magnitude we want?
We divide it.
Yeah, divide it by that magnitude. And geometrically, the reason this works S is a vector that has magnitude and direction. But what do you always get if you take a vector and divide it by its own magnitude? Like in this case, we've got a vector that's got magnitude square root of 17. Yeah, if you divide it by its own magnitude, if you divide this vector by square root of 17, you get a new vector that's a unit vector. Its magnitude is exactly 1, but it still has the same direction. So S divided by its own magnitude, this gives you a unit vector in the direction of S. So it keeps the direction we want, but it cancels out its own magnitude. So this is just a unit vector in the correct direction. So this is the S over magnitude S. This essentially is just a direction with magnitude 1 times the magnitude we want from trigonometry. This will give us a vector that's got the correct direction and the correct magnitude. So that's everything we're going to need. Any questions on that so far? And one other abbreviation we can make here, in the denominator, if we actually combine these, we've got magnitude S times itself. In other words, magnitude of S squared. What else is magnitude of S squared equal to? Can you write that as a dot product?
Is magnitude square like it's like just like and without the square root?
Well, how do you calculate a magnitude in the first place?
It's like a number squared plus a number square and then like the square root of it.
Yeah, like if you want to find the magnitude of xy, you take the square root of x squared plus y squared. But you could also think of that as a dot product. If you were taking the dot product of xy dot itself, you'd be multiplying x times x plus y times y. So that is x squared plus y squared. Which means you can always think of magnitude of a vector as square root of the vector dot itself. Which means if you square both sides, you get magnitude squared equals the vector dot itself. So magnitude of S squared is the same as S dot S. This is often a very useful way of rewriting a magnitude. Magnitude of a vector can always be written as square root of the vector dot itself, or anytime you have magnitude squared, that is just the vector dot itself. Which means we can write this whole thing in terms of dot products. The numerator is S dot V, that is the vector spanning the line we care about, dot the vector we're using as an input. The denominator is S dot itself. So this gives us a general formula for any projection, at least any projection of a vector onto a line. Anytime you're projecting a vector onto a line, you can always write that as S dot V over S dot itself times that vector S again. So in general, again, assuming V is the input vector and S is the direction you want to flatten it onto, you can find that by taking this scalar multiplier, S dot V over S dot itself, and multiplying by S, the direction you care about. And the reason this works, the times S, just a scalar times S, guarantees that the result will be in the same direction as S. But the S dot V over S dot S corrects for the magnitude using the trigonometry of this right triangle to guarantee you have this adjacent side as the result. So again, the times S guarantees the right direction. The times this scalar multiplier guarantees the right magnitude to get the projected vector. Any questions on that formula so far? Or alternatively in words rather than symbols, because I know the symbols can get kind of confusing since we use so many letters to represent so many vectors. You could think of this as direction. If you think of S as the direction you want, direction dot input So if you think of V as the input vector of the projection function, and S is the direction you're trying to create, direction dot input over the target direction dot itself times direction vector again. So this scalar creates the direction dot input over direction dot itself creates the correct magnitude when multiplied by the direction vector to get the correct direction. Any questions on that formula or where it comes from? Then let's try applying that to this specific example where we have our input vector 3, 4, and the direction we want to create 4, -1. Let's try actually applying this formula to that situation. So in general, the projection of some input vector onto some direction is always going to be direction dot input over direction dot itself times direction vector again. And by the way, dot product is commutative. You can change the order. So this top number, the numerator can be written as S dot V or V dot S, either one, same thing. So let's try running the calculations here. If we have vector V is 3, 4, that's our input vector, and vector S describing the target direction that we want to flatten it onto is 4, -1. Then let's calculate each piece of this individually. S dot V and S dot S. What would S dot V equal if you're taking the dot product of these two vectors?
Eight.
Yeah, 3 times 4 plus 4 times -1 is 8. And what about S dot itself?
$17.
Yeah. 4 times 4 plus -1 times -1, 17. And notice that the square root of that would be the magnitude, because magnitude is always square root of the vector dot itself. But in this case, we just need S dot S, so that's the magnitude squared. Any questions on those calculations so far? So the actual projection of V onto the direction of S is going to be S dot V, which is 8, over S dot itself, which is 17, times vector S itself, which is 4, -1. So multiplying that out, we get 8/17 times 4. That'll be 32/17. And 8/17 times -1 is -8/17. Or as mixed numbers, 32/17 is a little bit less than 34/17. So that's 1 and 15/17, almost 2. And -8/17 is a little bit less than 1, -1/2. So if we plot this on our graph, let me draw this a little bigger. So our original vector v was 3, 4. Our original vector s was 4, -1. And remember, the size of vector s doesn't matter. The whole point of it was to define a direction. But then our projection was 1 15/7, sorry, 15/17. So a little bit less than 2, and -8/17, so a bit beyond -1/2. So about here, which means from the origin to this point, this will be the projection. In other words, that projection vector is vector v flattened onto, or casting a shadow onto, the direction of s. And note the error vector, the difference between these is forming a right triangle. It's perpendicular to the original vector s, the direction. So we now have the projection vector, the original vector is projection onto line s, and also the error vector if we need it. Any questions on that so far? So that's how to calculate a projection. If you have a vector that's not on some line and you want to project it onto a line, you can always use this formula. This only works for one-dimensional projections. If you're projecting it onto a one-dimensional space, that is a space spanned by a single vector, then this formula should work. And there's a more extended version of this formula involving matrices that can be used for projecting onto a plane or a larger subspace, but this should work for lines. And a couple of the things I want to mention here. In this case, we had a vector that was just on some diagonal with respect to s. But let's take a look at a couple of special cases there. First of all, you get something interesting happening if the original vector v is perpendicular to the line. Like, let's say we had vector v was, what would be a vector perpendicular to 4, -1?
-1, 4.
-1, 4 would be this way. What we want is a vector this way. So what would that have to be? If we want it to be perpendicular to 4, -1. What has to be true about the vectors in order to count as perpendicular to each other?
The dot product equals 0.
Yeah, so if we have a vector dot 4, -1, and we want the result to be 0, what are some numbers that could make that work? I think you were almost there with the -1 and the 4, but be careful about the signs.
Is 1, 4 okay?
Yeah, 1, 4 should work, because then 1 times 4 plus 4 times -1, that's 4 minus 4, so that's going to be 0. So let's say v is 1, 4, just as an example. If we want the projection of that vector onto set S, or the span of S, we've got the same formula, but what's S dot V going to be?
0.
And 0 times any vector is going to be
0.
Yeah, the 0 vector. So this gives us an important fact about projections. If the v vector is orthogonal to the s vector, then the projection of v onto s is going to be the 0 vector. Because if we take that perpendicular vector, again, if you think of this as casting a shadow, if you've got a stick pointing like this and you've got light shining down like this, what would the shadow of that stick look like? Or if the sun, like let's say the sunlight is directly overhead and you've got a vertical stick, what sort of shadow is cast by a vertical stick if the sun is directly overhead?
Flat onto like the ground.
Not just flat. I mean, you could say any shadow is flat, but what shape would the shadow be? If the stick is genuinely perpendicular to the ground and the sunlight is directly overhead. If this perpendicular vector gets flattened onto the line, what's left? If you flatten this onto the line, what do you get?
Nothing.
You get nothing at all. If you've got that vertical stick and sunlight shining from directly overhead, the shadow is just a single point at the bottom of the stick, essentially no shadow at all, or a zero-dimensional shadow. So this is one of the important properties of projection. If you've got a vector that's orthogonal to not just necessarily a line, but a vector that's orthogonal to the subspace you care about, the projection onto that subspace is just going to be a single point, the zero vector. So this is one way of checking if a vector is perpendicular to a surface. Find the projection. If the projection is zero, that means the original vector was orthogonal to the surface. And another important result here, what would happen if vector v is already part of the surface we're talking about? Like, let's say vector v is already in the same direction as s. Geometrically, what would you expect the projection of s, or the projection of v onto s to look like? If you've got a vector that's already a member of the subspace and you project it onto the space. And again, if you think of this in terms of shadows, let's say we've got some vector that's already part of the board. If this marker is already part of the board, what can you say about the size of its shadow? In fact, I think you can see this, right? This is casting a shadow onto the board. If I flatten this onto the board, what happens to the size of the shadow versus the size of the marker?
It's the same.
Yeah, it's the same size. If this was perpendicular, assuming we have light shining straight in, which isn't quite the case, but if it's perpendicular, then we should expect no shadow at all. But as we flatten it onto the board, the shadow gets closer and closer to the size of the marker itself. And again, this doesn't quite work because I've got light coming in from over here rather than straight in. But if you got a marker that's on the board, its shadow is the same size as itself, which gives us another fact. If V is already a member of the subspace, then the projection of V onto that subspace is just V itself. There's no need to change vector V, because the whole point of a projection is to create a new vector that's in the subspace. But if V is already in the subspace, then the projection doesn't need to change it at all. So the projection of a vector that's already a member of the subspace is just the original vector itself. So these, I think, are probably two of the most important properties of a projection. That the projection of a vector perpendicular to the subspace is always going to be the zero vector. The projection of a vector that's already a member of the subspace will be just the original vector itself. Any other questions on that? All right, we are out of time for today, but if you have any other questions, like the projections of a matrix, yeah, email me about that and we can go over that next time, or we can talk about it in the Discord. And I will see you then.